Okay, perfect. I'm recording now. Okay, so yeah, so the idea, guys, just to remind you the idea. So the spread of the data, um, you know, about the mean, uh, is small if, right, if the standard deviation is small, if standard deviation is small. So again, the idea is what you need to keep in mind, guys, is that the standard deviation actually measures like the average distance from your data value to the mean. Okay, that's exactly like the definition of a standard deviation. Okay, so standard deviation is just the average distance between a random data value and your mean. Okay, and again, the idea is if you have a data set, you have numbers. So when you pick a random number, the expected number is always the mean. That's what you expect, right? And so this standard deviation actually measures distance between your random data value and your and the mean and the expected number. Okay, so the spread above the mean is of the data above the mean is small if the standard deviation is small, and the spread is large, of course. So the spread of the data value above the mean is large if the standard deviation is large. Standard deviation is large. So now, of course, we know how to compute. I mean, last week we discussed the steps how we compute the standard deviation, right? So now we know how to compute the standard deviation. So is large. Okay, so again, the idea is that, so the standard deviation, that's the average distance, standard deviation. This is just the average distance from the data values to the mean. All right, so we had the, you know, we have this, just to remind you an example with the flower diameters. So we have this example. So we have a random sample. Right, of two random sample of two, you know, two hybrids, you know, of flowers diameters. So this example was discussed last week, right? We discussed this example last week. Just to remind you the values here. So we had like two hybrids. There's a hybrid A and there is a hybrid B. It's hybrid A, hybrid B. And we said, so like in the hybrid A, so we have 6 flowers and the diameters in inches. Okay, this is very important, the diameters in inches. All right, so the hybrid A, we had like a 2, 3, 3. The fourth flower, its diameter is 8 inches. The fifth flower, its diameter is 10, and then again 10 inches. And the hybrid B, we have like 5 inches, 5, 5, 6, 7, and 8, right? And then we computed, I think, oops, and then we computed the standard deviation of the both hybrids. At least I think I went over the computation for the standard deviation of hybrid A at least. Okay, but anyway, so we said, just to remind you the answers here. So we said the answers here. So we said the standard deviation of A. Standard deviation of A So I think we said this is a 3 point, I think it's a 3.74, right? So S here, so S is 3.74 inches, okay? And standard deviation of hybrid B, I think we said 1.26 deviation of hybrid B. So S is, I think we said it's 1.26 inches. All right. And yeah, so the standard deviation of the hybrid A is larger than the standard deviation of the hybrid B. And so we said it means that the hybrid A is more dispersed than hybrid B, right? The hybrid A has more variation than hybrid B. Right. So our conclusion. So the standard deviation of hybrid A is larger than the standard deviation of hybrid B. So then the hybrid A is more dispersed. Than hybrid B. All right. All right. This now you want to, we have two random samples, and you want to compare their standard deviation, right? To see which sample is more dispersed, or which sample is more constant than the other one, right? Now, there's a problem with the standard deviation because, the answer here for the standard deviation, we use the units, right? Like here, the standard deviation of the hybrid A, it's a 3.74 inches, right? Same for hybrid B, it's 1.26 inches, right? So we use units to express the standard deviation, right? And that's a problem because, so what we are saying here is that your standard deviation depends on the unit, right? Your standard deviation depends on the unit. So like here, the unit is inches. So your standard deviation depends on the units, which is inches, okay? Now, the problem is, if you have like two random samples, okay? Two random samples, but of like different population, right? So for example, you have a first data values or first data set, and your first data set or first sample represents, for example, your flowers diameters, okay? And then you have a second data set, which actually doesn't represent the flowers diameters, but let's say it represents something else. So for example, it represents the speed of the cars on the highway, okay? So you have two samples or two random samples, and the samples actually represent different population, okay? Different different population. That's not the same thing. So like in the first sample, we have flowers, and the second sample, we have the speed of cars, right? So the units are different, right? So like the first sample, the unit would be inches, and the second sample with the speed of the cars, the unit would be miles per hour, right? So we're gonna have like two different units, right? So if you have like two different units, then you cannot compare the standard deviation of the two samples because you are using different units. And the problem is, again, your standard deviation depends on the units, right? So the thing about the standard deviation, so here, remark, so the standard deviation depends on the units. The standard deviation S, so the answer, your answer is going to depend on the unit. Standard deviation S depends. So the key word here, depends on the unit or units, okay? And if it depends on the units, then you cannot compare. So then we cannot compare. So we cannot compare two samples from two different populations. We cannot compare samples from from different populations. So in other words, you're using, like if you use like two different units in the first sample, you have two samples, right? And you're using two different units, then you cannot really compare the standard deviations. You cannot say, well, the first standard deviation is larger or less because you're using two different units, okay? So from different populations, because we are using different units. Okay, and that's a problem. So you need something which actually independent of units. So if you have something which is independent of units, then you can compare your data values even if the units are not the same. Okay, so we need something. So we need a notion independent of units. Okay, and that's exactly what the coefficient of variation does. So phi. So we had the range. Remember, guys, to measure the spread of your data, you can use the range. You can use the standard deviation, right? And now phi we can use. So this coefficient of variation. Okay. So the thing about the coefficient of variation, so it's unlike the standard deviation, coefficient of variation is going to be independent of units. Okay. So then you can compare measurements of different population using different units. Okay. So so the idea here, so this is the coefficient of variation is going to be independent of units, right? So unlike standard deviation, the coefficient of variation so this coefficient of variation is denoted by so C V, right? So C stands for a coefficient, of course, and V stands for variation, is independent. So this is independent of units. Okay, so then we can compare. We can compare measurements of different populations. Okay. Any question, guys? Makes sense to you? So now, of course, so now what's the formula of the coefficient of variation? Actually, coefficient of variation is going to depend on the standard deviation. So the only thing we're going to do, we're going to try to get rid of the unit. Okay. So so here's the formula for the coefficient of variation. So it's basically the standard deviation. So formula of coefficient of variation. So C V. So this is equal to S, the standard deviation, S over the mean, X bar. And then we need to multiply by 100. Multiply by 100. And that will give you a percent, so 100%. So the S here, guys, S is, so where S is, so S, that's the standard deviation. So if you want to compute your coefficient of variation, you need to compute your standard deviation. The X bar, it's just the mean, okay? And then all you have to do is to multiply by 100, all right? Let's have an example. So example. Okay. So I'm gonna compare data values of two different populations. So let's say we have two samples. Okay. So first sample is represent. So the first sample, I'm gonna just use the same example with the flowers diameters. So first sample is our hybrid A. So represent flower diameters in inches, right? So the example we had, where's the first example? Hybrid A. So we had 2, 3 inches, 3 inches, 8, 10, and 10. Okay. And again, guys, the thing is, when I say here 2, this is supposed to be 2 inches, right? So the data values here, they depend on the units, which is the inches here. Okay. When I say 3, this is supposed to be the flower diameter, right? So this is like 3 inches. Okay, the data values depends on the units, okay, etc. So this is my first sample, okay, and we actually computed the, it's a standard deviation, right? We said it's a 3.74 inches. All right, so we know we computed S. We know that S. So S in this case, we said it's a 3.74 inches. Okay. And what's the mean here? What's X bar? And the mean, of course, the mean also depends on the inches, right? So the mean is supposed to be like, 2 plus 3, the sum of all data values over the number of data values, right? So we have like 2 plus 3, plus 3 plus 8 plus 10 plus 10, and we're gonna divide by 6 because we have 6 numbers or 6 flowers. So 6 divided by 6. So that would be 36 over 6, and that's equal to 6 inches. So the mean, the unit, so the mean depends also on the units, right? So the mean here, it's 6 inches. Okay, so just to emphasize here, so the mean depends also on the units. Depends on the units. Right. Anyway, so this is your S. It's 3.74 inches. This is your mean. It's actually 6 inches. Okay. This is my first sample. Okay. Now, what's the coefficient of variation of this first sample? So let's compute. Let's compute the coefficient of variation. All right, so we said coefficient of variation is going to be equal to S, right, over X bar, the mean, and then we need to multiply by 100. Okay, and then we are supposed to put like a percentage, symbol. Okay, so like here in this example, we'd have S is 3.74, the thing is, guys, like in this example, the S, the standard deviation, right, depends on the units, right? It's supposed to be 3.74 inches. And the X bar, which is 6 inches, right? The X bar, the mean, depends also on the units. So like you're gonna have like a fraction where the top depends on the inches and the denominator is gonna depend on inches. So then the idea is when you divide, then the unit is gonna cancel out. So the inches here is gonna cancel out. Okay. So the idea is when you divide your standard deviation by the X bar, by the mean, you're gonna get rid of the unit. Okay. That's why the coefficient of variation is independent of units. Okay. So yeah. So what I'm saying is, so because S and X bar both depends on the unit inches. So then when you divide S by X bar, you get rid of the units. So then S over X bar is actually independent. And it's going to cancel out independent of the units. All right. So that's the idea. Anyway, so let's finish. Yes. I didn't finish yet the coefficient of variation, right? So it's a 3.74 inches over X bar, which is 6 inches, right? And as I said, the inches, they're gonna cancel out. Then times 100, right? And then there's a percent symbol, right? So the coefficient of variation in this case, so you just divide using your calculator. Oh, there's this question in the chat, sorry. Oh, Kayla, okay, I got you, thank you. So when you divide S by X bar, so we divide 3.74 by 6, okay, you're gonna get like 0.62, I think 3, okay. So that's what we get when you divide 3.74 by 6. And then we need to multiply by 100. So we need to multiply, this is multiplication here. This is multiplication by 100. So we need to multiply by 100, okay? And then there's a percent. So it's 0.6233 times 100. So that will be 62. So your coefficient of variation is going to be 62.33, okay? And then there's a percent. So 62.33%. So your coefficient of variation is actually, it's a percentage, okay? So you divide S by X bar and then just multiply by 100. Then you get your coefficient of variation, okay? And again, it's a percentage. You see here, there's a percent symbol here, okay? So so in this example, my coefficient of variation, it's just a 62.33%. Okay. All right, so that's the coefficient of variation of this first sample. And as I said, this sample represents flowers diameter. So the unit's supposed to be inches. All right, so now let's say we have a second sample, and this second sample is from different population. So it's gonna represent, so we have a second sample. Second sample, okay? And this second sample is gonna represents, let's say, the number let's say the number of injuries in, let's say, 6 different teams in the, let's say, uh, in the NHL. Okay. So for example, let's say we have six, so we have six different teams. And so let's say the first team has like the first team has, let's say five injuries. Second team has like five injuries. And again, let's say five, 6, 7, and 8. Okay. So in this example, the unit, of course, in this example, the unit is not, it's not inches anymore, right? So in this example, in this sample, the unit, it's a number of injuries, right? So it's like a first team in the first team has like 5 injuries last season, let's say. So the unit here, it's injuries, right? So it's 5 injuries, right? So the unit, the unit here is, so it's 5 players, right? Is injuries, players. Okay. But anyway, the idea is we are using different unit than the first sample. Okay. Now, the standard deviation of this example, would be 1 point. So standard deviation of this example. So standard deviation S. So in this example, it's going to be 1.26, right? But it's not 1.26 inches, it's 1.26 injuries or players. Okay. And X bar of this sample. So again, it's just 5 plus 5 plus 5 plus 6, 7 plus 8 over the number of teams. We have 6 different teams, so over 6. And I think it's going to be 15, 21. It's 36, right? I think it's 36 again over 6. So the mean, it's 6 players. Okay. Now, what will be the coefficient of variation in this example? So then the coefficient of variation, CV, so CV in this example. So again, it's just S over X bar, just divide S by X bar, and then we multiply by 100. And then there is a percent, because this coefficient of variation is going to be percentage, right? So, so like in this example, S is, we said it's 1.26 over, so here this is multiplication, of course. This is multiplication here. So 1.26 over 6 times, multiply by 100. Okay, and then there is a percent. So 1.26 over 6, if you just divide 1.26 by 6, I think it's 0.21. So it's going to be like 0.21. Okay. Again, this 1.26 over 6, right? So it's going to be 0.21. And then you need to multiply by 100. Percent. So 0.21 times 100, if you multiply by 100, that will be 21. Okay. And so the answer would be 21%. Okay. So this is a coefficient of variation of the second sample. All right, so now you can compare the coefficient of variation of the 2 samples. So again, the 2 samples represent different populations, right? In the first sample, we had the flowers. The second sample, we have NHL players, right? In the first sample, the coefficient of variation is 62.33. okay? And the second sample, the coefficient of variation is 21. Of course, the coefficient of variation of the first sample is larger, so than the coefficient of variation of the second sample, right? So the conclusion here, so what we can say is, so the coefficient of variation of the first sample, which is 62.33%, right, is, of course, this is larger than 21%, is larger than coefficient of variation of the second sample, which is 21%. We just proved that it's actually, we just computed, it's actually 21%, right? 21%. So, so if the coefficient of variation is larger, of the first sample is larger than this is the coefficient of variation of the second sample, then again, the conclusion is that the first sample is more dispersed, okay? Has more variation than the second sample, right? So so the conclusion is, so the first sample is more dispersed. Again, so it's more dispersed or has more variation than second sample. All right. So again, the idea here, guys, is that, so if you have two samples and you want to compare the two samples, you want to compare the spread about the mean of the two samples, okay? And the two samples, they come from different populations, right? Like here, first sample is flowers, second sample is like NHL players, all right? You cannot use the standard deviation to compare the spread of the two samples because the standard deviation would depend on the units, all right? So you need to use the coefficient of variation, okay? Does this make sense to you guys? I mean, I hope makes sense, right? So,
So I'm sorry to
yes.
Just revise real quick.
Yeah.
First, I have to find the standard of deviation.
Yes.
Find the mean, and
Yeah.
then perform the formula to do this stuff. Obviously.
Yeah. You divide the standard deviation by x. Of course, here the examples. I mean, we already computed the standard deviation, right? Because it's a lot of computations, right? Yeah, so you divide the S, the standard deviation, by X bar, the mean. You multiply by 100, right? And you get your percentage. That's your coefficient of variation.
Okay, thank you.
Do we have time for an exercise?
And on the, I'm sorry, and on the test, it would be stated the same way. It would be cohescent. What did I write it? The name of this. It would not say, because the reason I'm asking is usually in math tests you have like a problem, and then I don't want to get confused where the terminology is different.
Yeah, I mean, like in the test, of course it's gonna well, like in the problem, you'll see it's gonna ask you, like, for example, to compute the standard deviation, then the X bar, and then if needed, it's gonna ask you to compute the coefficient of variation, okay? And then it's gonna ask you to use the coefficient of variation to compare the spread of the two data values. Yeah, so I mean, it's gonna be clear what you need to do in the test. It's gonna tell you compute the coefficient of variation. So you need to, of course, you need to know the formula, and that's it. I mean, I don't see how you can get confused in that case. I mean, if it tells you, yeah, yeah, it's gonna be kind of clear what you need to do in the test. Yeah. All right, so we can do an example or an exercise. Is the formula for homework 3? Which
it's me, Professor Taylor, because I missed I missed the beginning of the class. You know how you put
So
the
this,
homework
no, no,
out?
this, you don't need this formula for homework number 3. So actually for homework
Okay.
number 3, you're gonna need the standard deviation, but then we discussed the standard deviation last week. So this is not, this is not related to the homework number 3.
Okay, this is something completely different. It just looks similar.
Yeah, it looks similar because we are
Okay.
using the same information as the S, the standard deviation, but this coefficient of variation, it's not in the homework 3.
Okay, I'm gonna review the video.
Sure. All right, guys. All right, so let's. Well, I don't think probably we don't really need to do an exercise here, because once you know how to compute the standard deviation S and X bar, right? Then just to divide this S by X bar and multiply by 100, right? So I don't think we need really to practice this, unless someone has like a problem and is confused about this formula. But I think it's straightforward, right? Once you have your S, your standard deviation, and X bar, right? Then it's kind of, the formula is kind of straightforward. Just divide and then multiply by 100. All right. So all right. So next. So next we're gonna discuss the Chebyshev's theorem. So next. So next we're gonna discuss the Chebyshev's theorem. Okay. All right. So what's this Chebyshev's theorem? So the idea is the following. So this Chebyshev's theorem is going to give you. So the idea is the following. So the Chebyshev's theorem gives you the proportion of data. So gives the proportion of data okay, that must lie within a certain number of standard deviation and certain number of standard deviation above the mean. Above the mean. Okay, so it's going to tell you, this Chebyshev theorem is going to tell you exactly the proportion of data that must lie within a certain number of standard deviation above the mean, right? So again, the idea is here, we're going to use this standard deviation to measure, the distance from your data values to the mean, right? And this Chebyshev theorem is going to give you exactly the proportion of data that must lie within a certain number of standard deviation above the mean. So I'm gonna, before the theorem, I'm gonna just first, I'm gonna start with the consequence of the theorem. Okay, so the idea is the following. So we're gonna have some consequences from this theorem, and so for example. So I'm going to discuss the consequences of the theorem, and then I will write down the theorem, okay? Of Chebyshev's theorem. So consequences of Chebyshev's theorem. For example, so this Chebyshev's theorem is going to tell you first. So, so I was going to tell you that at least, and at least here it's an important word, okay? At least means like the minimum, right? At least that's like the minimum. So at least, for example, at least 75%, 75% of your data values are between your mean, so mean, the mean minus 2 sigma or minus 2s, minus 2 times the standard deviation, minus 2 times the standard deviation, and the mean plus 2 times the standard deviation. Okay. So in other words, 75%. So in other words, so this is Chebyshev's theorem is going to tell you that at least 75% of data values, they fall in the interval. They're going to fall in the interval and the mean minus 2 times the standard deviation. So the mean x bar minus 2s and the mean plus 2s. Okay. So what does it mean? This 75% of data values are between, at least 75% of data values are between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Let's have an example, okay? Example, numerical example, right? So again, we're gonna have the same example of the flowers diameters, all right? So this, so we have this sample which represents flowers diameters, okay? And we have 6 numbers, right? I mean 6 flowers. So we have like, let's say this, we have 2, right? We have 3, we have, and then we have 8, 10, and then 10 inches, right? This unit here is inches, diameters in inches. All right, so that's my sample. So what I'm saying is, we computed X bar, right? The X bar, the mean, we said it's X bar is 6 inches, right? The 2 plus 3, you know, we know how to compute the mean, right? X bar, you know, 2 plus 3 plus 3 plus 8, 10 over, we have 6 flowers, so over 6, and we said it's 36 over 6, and we said the mean is 6 inches, right? That's our mean, X bar, okay? And what we are saying, and then we computed the S, right? The standard deviation S. We said S is, where's S? S, we said S is 3.74 inches. Okay. So what does this Chebyshev theorem say? Well, it says like, we know for a fact that at least 75%. So we are saying, so the Chebyshev theorem says like, so the Chebyshev's theorem says that at least So again, at least here means minimum. Okay, the minimum. Okay. So at least 75% of your data values. So what does it mean 75% of data values? So how many data values we have? We have 6 numbers, right? We have 6 flowers or 6 numbers, right? So 75% of data values, that's 75% of data value. So that's 75% of the six flowers. So, so in other words, 75% of the 6 flowers. So of, the word of, it means multiplication. So 75% of the 6. So times 6. Okay. Of the data value. So the 75% of 6, that's equal to 75%. The percent means division by 100, right? The percent, that's division by 100. So this is like 75 over 100, right? Times 6. Okay. So 75 times 6 over 100, that's equal to, 75 times 6 over 100. 75 times 6, that will be equal to what? So we have 450 over 100, right? So that's 4.5. Okay. So 75% here of data values means 75% of your 6 flowers. So that's 4.5 flowers. So 4.5 flowers. Okay. So what we are saying is at least 4.5 flowers. Okay. Their diameter is between X bar. We said X bar minus 2s and X bar plus 2s. So the diameter of 4.5, at least 4.5 flowers. Let me write it down here. So the diameter of at least 4.5 flowers is between X bar minus 2s. So X bar, we said it's 6 inches minus 2s, that's minus 2 times, 3 point, s is 3.74, right? The inches, s is 3.74. So 2 times 3.74 and X bar plus 2s. So that's 6 plus 2 times 3.74. Okay. So that will be equal to, so 6 minus 2s, or 6 minus 2 times 3.74. So that's 6 minus, we multiply PEMDAS rule, of course. We need to multiply first. So we need to multiply 3.74 2. Okay. So that will be equal to, so we have 8, and then we have 4. So that's 7.48. Okay. And here it's 6 plus 7.48. Okay. And then 6 minus 7.48, when you subtract, so it's going to be a negative number, right? So it's negative 1.48, and here is going to be 13. 0.48. Okay. So what we are saying here is that at least 4.5 flowers. We have 6 flowers actually, not 4.5. 4.5 means like 4 flowers and a half. But so we have 6 flowers. But we are saying is at least 4.5 flowers, their diameter is supposed to be between negative 1.48 inches and 13.48 inches. Actually, how many flowers their diameter is between negative where is it? Sorry. Here. So how many flowers the diameter between negative 1.48 and 13.48 inches? Well, as you can see, the diameters is like they are from 2 to 10. Okay, so all the flowers here, their diameters is is between negative 1.48 and 13.48. Okay, but the theorem says like at least 4.5. So here we have more than 4.5 flowers with diameter between negative 1.38 and 13.48, right? So actually all the flowers. That's why we are using the word at least, because that's like the minimum. The minimum is 4.5 flowers with diameter between negative 1.48 and 13.48. Okay, but actually the truth is all the flowers has the diameter between negative 1.48 and 13.48. Okay, so actually all the flowers. So actually the diameter of all the flowers, the diameter of all the flowers is between negative 1.48 and 13.48 inches. Okay, not just 4.5 flowers, but all the 6 flowers, their diameters is between these two numbers. Okay, so you see, the theorem predicts the minimum of the flowers with diameter between these two numbers. Okay, so the theorem says like at least we have 4.5 flowers out of 6 with diameter between these two numbers, between this negative 1.48 and 13.48, right? But of course here, as we can check, all the flowers, their diameter is between these two numbers, not just 4.5 flowers. Okay. So again, the theorem is going to give you like the prediction of the minimum of your data values between between two numbers. Okay. And the numbers here are, of course, the negative 1.48 and the 13.48. That's depends on the X bar and the standard deviation. Okay. So we can do better than 75%. So here we said like as a first consequence of this distributive theorem, we can say that at least 75% of the data values are between X bar minus 2s and X bar plus 2s. So we can do better than 75%. So for example, consequence number 2, and then I will write down the theorem. So the theorem says like at least, so if you want to do more than 75%, you can do 88.9% of your data values fall in the interval X bar minus ds and X bar plus ds. Okay. You can do better than 88.9. Actually, you can do 93%. And I will show you why this is a consequence of the theorem. I didn't write theorem. Okay, you can show that using the theorem, you can show that at least 93% of your data value, they're gonna fall in the interval x bar minus 4s and x bar plus 4s. So as you can see, guys, here, when you change the percentage of your data values, here it's 88.9% of your data values, here it's 93. Then you're gonna increase the distance from the mean. So the distance here from the mean is three times the standard deviation. Here, the distance from the mean, it's 4 times the standard deviation. Okay. Anyway, so let me write down now the theorem. This is just like, I mean, it's just to give you an idea about the theorem. But the theorem says the following, actually. So the Chebyshev's theorem is the following. So it says the following. So for any data set, for any data set, okay, it doesn't matter if it's it doesn't matter if it's a sample or a population, okay? And for any positive whole number, k, and for any positive whole number or integer k, okay, larger than 1, okay, the proportion of data so the proportion of data that must lie within k times standard deviation on either side of the mean. Either side of the mean is either side of the mean is 1 minus is at least 1 minus 1 over k squared.
Oh, come on.
Okay. All right. So for example, if let's say k is 2. Okay. So for example, if k is 2. So consequence for examples. Let's say k is 2. Okay, that's a positive. You take a positive whole number larger than 1. Okay, so that would be first the positive whole number larger than 1, of course, would be 2. So if k is 2, so again, the theorem says the proportion of data that must lie within 2 times, so k is 2, right? 2 times the standard deviation on either side of the mean is at least, so the proportion of data that must lie. So again, k is just you pick a positive, positive whole number, right? Larger than 1. So here I just picked k equal to 2. Okay, so the proportion of data that must lie within k times the standard deviation. So in this case, k is 2. So 2 times the standard deviation on either side of the mean. On either side of the mean. Side of the mean. Right. So like, you have this is your number line. somewhere you have the mean, right? X bar, okay? So like in my previous example, X bar is 6 inches, right? Now I'm gonna take 2 standard deviation from the mean on the left and on the right. So here, let's say this is like X bar minus times the standard deviation, and this is like X bar plus 2 times the standard deviation, right? So here's my interval. This is your number line. Okay. And yeah, so either side of the mean is at least, and it says 1 minus 1 over k squared. So in this case, k is 2. So that's k is 2. So that's 2 squared, right? So like this would be 1 minus 1 over 2 squared. It's 2 times 2. That's 4. So 1 minus 1/4. Of course, you're going to need the common denominator, right? Common denominator. So then this one here, you make it look like a fraction. So this is like 1/1, right? And then common denominator would be 4. So you need to multiply by 4, like here by 4. Okay. So that's like 4/4 minus 1/4. So that's 3/4. And what I'm saying is 3/4, that's the same thing. That's equal to 3/4. That's equal to, if you multiply by 25. Okay, that's equal to 75/100. Okay, and 75/100, that's 75%. Okay, so that's how I got this. You know, when k is 2, I get at least 75% of my data. Okay, which must lie within 2 standard deviation on either side of the mean. So that's how I got this first consequence of the Chebyshev theorem, right? I said as a first consequence, at least 75% of the data value is actually between the mean minus 2 standard deviation and mean plus 2 standard deviation, okay? So for each k, so like here in this example, I use k is equal to 2. So when I use k is equal to 2, I get, so the idea is, so if you use k is 2, then the percentage you get is 75%. If k is 3, the percentage you get is 88.9%. Okay. K is 4, the percentage you get is like 93%. Okay. So we can actually just forget about the theorem. Okay. Just we can just focus on the consequence of the theorem, right? So what we are saying is, so what you need to really keep in mind here, guys. So what you need to keep in mind, and what we're gonna use in the examples and the homework, okay, is the following. So so we need to know the consequences of the theorem, right? So first, so what we are saying is at least when k is 2, as I said, we get 75%. So at least 75% of data must lie within, or must fall in the interval interval x bar minus 2s and x bar plus 2s. Okay. If you want to do better than 75%, you can go with k is 3, and that will be 88.9%. So at least 88.9% of data must fall in the interval And now I have the interval x minus ts and x bar plus ts minus ts and x bar plus p times s. Again, the x bar is the mean and s is the standard deviation. If you use k is equal to 4 in the theorem, then the percentage you get is 93%. But then, of course, you're going to have like a bigger interval. So that will be the interval x bar minus 4s. So if k is 4, so this is when k is 2, this is when k is 3, and this is like when k is 4 in the theorem. Okay. So if k is 4 in the theorem, then the consequence is that at least 90% of the data must fall in the interval x bar minus 4s and x bar plus 4s. Okay. Again, guys, the word here at least is very important. So when I say at least, that's like the minimum, right? So of course, you can have more than 75% in the interval x bar minus 2s and x bar plus 2s, okay? But the minimum is 75%. At least of 75% of your data, of your numbers, are actually between the x bar minus 2s and the x bar plus 2s, okay? All right, so I'm going to do a lot of examples because I know this is kind of confusing. But again, what you really need to keep in mind here is these percentages. So if you see like in the problem, you need at least 75% of your data value, then this is the interval you need to use, the x bar minus 2s, x bar plus 2s, right? If you see like in the problem, you need at least 88.9% of your data value, then this is the interval you need to use, the x bar minus the s, x bar plus the s, okay? So, so for each percentage here, you have a different interval, right? And I mean, like here we have 3 different percentages, like 75%, 88.9, etc. And for each percentage, as you can see, there is like different interval, right? X bar minus the s, etc. Okay. Okay. Anyway, so with the examples, I'm sure it's going to be more clear because I know this is very confusing. But you see in the examples, it's not really hard. I don't think it's really hard. All right, so let's do a couple of examples and let's see how this theorem works, okay? Examples. Do I have time to do an example? Okay, well, it's 1 minute. Oops. Okay. All right, you know what? I'm gonna probably discuss examples tomorrow. Yeah, because I'm gonna need more than 1 minute for sure for one example. So yeah, let's do this tomorrow, okay? Examples tomorrow. All right, guys. Anyway, so I'm gonna stop here, okay? And we're gonna discuss the examples tomorrow. Thank you for listening, guys, and hopefully I'm gonna see you tomorrow.
Professor?
Yes,
Nice
yes,
one.
please.
Can I ask you a question?
Yeah, please.
I emailed you. I'm sorry when I was at work because I didn't want to forget, you know, what I was doing. So did you get my email with the homework on it?
Yes, homework fee.
So was I doing